You can go on a crime scene and you can decide like, oh yeah, this person did it, without doing any investigation whatsoever, if that person also admits to the crime, for instance. And you can do everything. You can spend like 3 years investigating. And both scenarios are very undesirable, right? So how do you decide that, this is exactly what they need to come to a confident decision and trustworthy decision? And yeah, it's fascinating. I like that.
Hello and welcome to the Pittcon podcast. In this episode, we sit down with Arian Van Asten to discuss the identification of illicit drugs and explosives using portable near-infrared spectroscopy. Could you please introduce yourself and discuss what led you to focus on the chemical analysis of drugs and explosives within forensic analytical chemistry?
My name is Arian Van Asten. I'm a professor in forensic analytical chemistry at the Van Hoff Institute of Molecular Sciences of the University of Amsterdam. Prior to that, I've worked for a very long time at the Netherlands Forensic Institute, and so hence my passion for forensic science. And I have a PhD in analytical chemistry, so put the two together, and then it's what I'm really interested in. I do a lot of projects. I'm also involved in microtraces, gunshot residues, that type of thing, but special interest, I think, in the analysis of drugs and explosives. And what makes them special actually is that these are chemicals with which people commit crimes, actually, right? So making money with drugs of abuse or abusing energetic materials to create explosions and stuff like that.
And building on that, could you briefly describe the main challenges that law enforcement agencies face in some on-scene chemical identification of drugs and explosives that are, say, being used in these crime scenes?
Yeah, if we start with illicit drugs, what we see actually is, for instance, here in the US is the opioid crisis. So how that translates basically for the forensic experts in the laboratory is that they see an increasing number of cases, so the caseload is very high. And in addition to that, also the chemical complexity of the samples that they need to analyze increases. It's more difficult to analyze them correctly. So there are multiple challenges that they face. With respect to explosives, in itself, that is a challenging area because of the chemical diversity that you encounter. So you have both organic materials, inorganic materials. So typically one single analytical technique does not suffice to characterize in a given case. And in addition, you have cases in which you have like intact explosives, which you call pre-explosion cases, but also after the fact, after the explosion. And then you get totally different kind of samples to analyze.
Oh wow, that's quite interesting. And how does your research hope to address some of these different things that happen?
Basically, especially the work that I've presented here just at the Pittcon conference, that is really aiming towards allowing people in the field to start doing chemical analysis. So use portable technologies that are actually really suited for use in the field, do not require high-end laboratory conditions for the analysis. So this is specifically focused on chemical identification, so the very rapid chemical identification of drugs and explosives, ideally in seconds, without people having to have any chemical knowledge or chemistry background whatsoever. That is basically one of... I do other stuff as well, but that is an interesting field. I try to advance forensic analytical chemistry.
I'm guessing it's so people can conduct those analyses right there on the scene rather than having to say,
exactly,
send them back.
Yeah, exactly. Yeah, that's the idea. Yeah. So basically, the challenge that I see for us as the experts is to create the methodology that would allow them to do it without making any error. So if it's too complicated, for instance, how to control the machine, then we have to make it simpler. So we have to, develop it into the next step. That basically you could also do like a very trustworthy chemical identification of, let's say, cocaine or heroin or an energetic material like TNT.
That's the thing, it's not always people who are, scientifically trained that are using these instruments, is it? So
yeah, well, I think I challenge my colleagues occasionally. Whenever somebody attempts to do something like that and they make a mistake, then in my field, people quickly say like, yeah, but that person did not study chemistry, so of course that person is going to make mistakes. But I will then challenge my colleagues. I say like, no, we should develop further to allow that person to do that analysis, because that's also how a computer works, right? Initially the computer could only be controlled by people that had a lot of knowledge, but nowadays everybody's using that technology, right? So that idea I want to bring to my field, basically. Yeah.
That's a really good point. So kind of building on these different methodologies and technologies you spoke of, what led to the selection of near-infrared spectroscopy as the primary technology for your research? And how does it compare to other portable analysis technologies out there?
Yeah, that's a good question. There are several options or routes that you can take, right? So you can mobile mass spectrometry, electrochemistry, colorimetric reactions, and then you have options in terms of spectroscopy. So you have Raman, infrared, and we choose the near-infrared spectroscopy. There are a couple of reasons for that. First of all, it lends itself very, very well for miniaturization. So you have very small, almost pocket-size near spectrometers, also being demonstrated here at Pittcon. And there are some additional very positive features to the technology. It's extremely rapid. So technology we work with, you create a reflectance spectrum in a few seconds. And so when people talk about rapid analysis, sometimes they introduce methods that take a minute or 2 minutes or 3 minutes. And if you talk to people that are in law enforcement or customs, then a few minutes on the scene doing a measurement can feel like a lifetime. It can be too long for them. So that I think is something that is very attractive to near spectroscopy, that it is really a matter of seconds. So within 10, 20 seconds, I can do multiple measurements on the same sample. So that is very attractive.
Mm-hmm. No, definitely. And speaking again about near-infrared technologies, how does the miniaturized MEMS near-infrared sensor integrate with existing law enforcement procedures for drug and explosive detection? And are there any really crucial advantages that these sensors convey for this application?
If you look at how it's done currently, let's take illicit drugs as the example, right? So often the first step, typically also in the field, is a colorimetric reaction. But that's already a little bit awkward, because then you have to add liquids to the sample, you have to observe a color. People have to do something with liquids or handle or dissolve a sample, and they are not trained to do so. So immediately that is awkward. With the sensor that we use, basically, and we use reflectance. So the only thing people need to do is to put the sample, the powder, enough of the material into a glass vial, put that on the sensor, and then press scan, basically. There is no sample preparation. It's not necessary. So that is very convenient in the process, right? So both in the field, but also in a laboratory situation where you do like high volume screening, where you are handling a lot of samples. So these are very positive aspects of the technique, I think. Yeah.
And can you elaborate on the dedicated data analysis strategy that you've been involved with, particularly the role of linear discriminant analysis and net analyte signal in improving the accuracy?
Yeah, that is where a little bit the magic comes in, right? So credits are due to Dr. Henk-Jan Ramaker from TIP, for which we work. He does a lot of the model development and the chemometrics, the advanced data analysis. It's also, I think, one of the challenges of the technique. So the thing is that if I'm in a forensic setting, I have a sample with an unknown composition. I have an idea that it could contain explosives or illicit drugs, depending on the context of the case. But I'm not sure. It's also not pure. There are other components there. So a typical street sample with drugs will contain, in addition to the psychoactive substance, several other substances, like adulterants, diluents, tableting agents, for instance. But I don't know this. So when I do the measurement, I get kind of a composite signal for all these components in there. But I'm specifically interested, of course, in this illicit drug or this explosive. So here we need the data science to help us, basically decipher the complex signal and let us know whether these compounds that we're interested in are actually there. You can take a bit more like a machine learning approach, but that requires huge amounts of data. So basically what we're then doing is that we're going to measure thousands and thousands of actual street samples for which we know the ground truth, so for which we have used other techniques like GCMS to determine the composition. And then we're going to use that knowledge to, if we have an unknown, to see okay, it's very similar to this signal, so it probably is this type of composition. What Henk-Jan has done is make that much more elegant, because that requires a huge amount of data, basically, to have functional models. So what he has done is basically, we take pure compound spectra of all the known constituents in a sample. So from research and cases, we know that there's like maybe 15, 20 compounds that you can find in a typical cocaine street sample, for instance. And we take the pure compound spectra, and with the NAS model, basically, he's able to try all sorts of combinations of that to arrive at something that fits very well with the measured signal, and then we have quite a nice estimation of the actual composition. And that is much faster and requires less reference data for us to have a functional model.
Oh, definitely. So one question I do have specifically about the samples is that, have you noticed an increase in complexity in samples over time? Or do you think maybe it's just instruments are getting better at characterizing just a large variety of compounds that are in a sample?
I think both are true, I would say. So clearly we have more analytical capability to really look at very low levels of what is in these samples, and to chemically understand what's going on. So materials degrading, or what kind of raw materials are used. It's a different kind of field that I'm also involved in, that is chemical profiling. So we're not so much interested in what is the main constituent. We're interested in these impurities and what they tell us about how the material was made, how the material was transported, these type of things. But you can't typically do that with portable spectroscopy. It's also definitely true that around the world, the chemical complexity of, let's say, illicit drugs, not so much for explosives, I would say, but specifically for illicit drugs, have become much more complex. And there's basically like two reasons for that. First of all, because many countries work with lists of banned substances in their law. We've seen like creative criminals creating psychoactive substances that just fall outside that list. So they create molecules that look very similar to banned substances, that are as psychoactive as banned substances, but they're not banned. So then basically you do not commit a crime according to the illicit drug law, at least in my country, when you put that onto the market. So what you then get, basically, is that governments respond. So when they see that this material is entering the illicit drug market, they put that compound also on the list. But that fuels kind of a rat race in which the criminal makes another variant. So we see a rise in what we call designer drugs onto the many European markets. And then, of course, you have really the crisis situation here in the US, where we see, or where they see, fentanyl, and sometimes 3-4 fentanyl variants in a street sample. So where 10 years ago it was like straightforward cocaine or heroin sample, nowadays they have to look at really low level whether there are any fentanyls there. So that's very specific for the US though. Yeah.
And do you find there's a lot of open communication between like governmental organizations and, say, researchers that are in your field that are conducting research into these different chemical profiles? Or do you think there still needs to be a little bit more work there to really tie up people? I
think definitely yes. I've working in the forensic science domain. That's really open. It is a bit difficult. So we are scientists, so we would like to explore and try new methods and develop and then share, of course, because then with that you can contribute to safe and just society. So everybody wants that. At the same time, especially when you investigate how to make explosives, for instance, or how to characterize drugs of abuse, there's always the risk that this information falls into the wrong hands. It can also be abused, right? So we have to be a little bit careful. But I would say typically forensic science is a very international, open environment where people share. It is the legal system that typically is very domestic and very local. So just to give an example, in the Netherlands, it's very difficult to enter, let's say, English forensic reports that have been written in English. Typically not accepted by the courts. They have to be translated to Dutch, because every legal system, right, criminal law, is typically very strongly focused on the language of that, and it is national, it's not international. Of course, you have international criminal courts, but typically criminal law is domestic. So the legal system is challenging us a little bit to exchange knowledge or services or capacity, whatever. but the scientists typically do collaborate a lot and share a lot of the findings.
Which is nice.
Yeah, well, the thing is, I'm not in it for the money, or I don't want to start a company or something. People that work in forensic science, they have an ambition and they have an energy to contribute something to society in terms of justice and security, right? So that gives a mindset of sharing, I think.
No, definitely. And if we can just go back to some of like the points you made about using, say, these different technologies and different applications to courts, how close is the current technologies that you use? How close are they to meeting the standards of forensic evidence admissible in court? And what are the main problems that need to be addressed to get to that point?
That is an excellent question. That's the $1 million question, right? Now, also there are a couple of things. So first of all, when you make that transition from science and development to something that is really used in forensic practice and is presented as evidence, forensic evidence in court, you need to be very strict with respect to quality. So you need validation studies, you need accredited methods, right? So you have accreditation bodies that come and check. So you need to make that method, that new method, fit for purpose, basically. You would have to show quite vigorously that you know the error rates, you know when things go wrong, you know how to spot an error and how to improve, and this is of course very important because once that evidence is in court, right, the impact it can have, you want it to be free of error. Of course, it's always, when people do stuff, errors are made. It's impossible to do anything. If you don't want to make any errors, you shouldn't do anything, right? But but at least you need to show that you're in full control, and it's just very important. It can make a lot of difference to people involved, right? Suspects, victims, family members. So you have to get it right. So that is something you always need to do. And then there's the interesting question, and this was also in my presentation, is when is it good enough? So when is there enough selectivity to say that with a portable technique you can do a measurement in seconds and also present that with confidence in court? And there you run against kind of, I would say, a little bit conservatism, right? So we've done it always in this way. I can't believe that it is that trustworthy if somebody does it that doesn't have a chemistry background. So that is something that I wouldn't say fight, but we debate, we challenge. I like to challenge that, but because I think, why do you think it is impossible to use such a technology? Because there are other examples. So whoever decided that the technology that you use today was fit for purpose? Because 50 years ago, that was very innovative as well, right? So that process of that step of innovation and development into really making a difference in court is a challenging one. So I think we need to rethink a little bit how we deal with this. And it's typical for forensic science because you can do nothing. You can go on a crime scene and you can decide like, oh yeah, this person did it without doing any investigation whatsoever. If that person also admits to the crime, for instance, and you can do everything. You can spend like 3 years investigating, and both scenarios are very undesirable, right? So how do you decide that this is exactly what they need to come to a confident decision and trustworthy decision? And yeah, it's fascinating. I like that.
It is fascinating. It's like, to what extent can we really use science, and can we depend on science to just get truth and to get fact of something? And science in a way, we should always challenge it, but we do take it as fact.
Yeah. Well, that's also a fascinating part of my work is that there's this kind of a clash, because if you're in court, right, then the judge or the people involved or the public prosecutor or the legal defense, they have a very simple question, right? Did that person fire the gun? Yes or no? And then in comes the scientist, and that expert cannot say yes or no. There's uncertainty involved always. And then that person starts to try to explain that, right? Try to explain uncertainty. And then everybody starts to look like, okay, you're the expert. Why are you telling this very difficult story? The question was super simple, right? Yes or no? And then, but I cannot, So that is fascinating as well. But yeah. So that is what we need to develop is it's an interesting aspect. So first there needs to be the science, then there needs to be the quality, and the assurance that the information that we bring is highly valuable and trustworthy. And then how do you communicate it, right? So that is interesting. Yeah.
And you previously spoke about your collaborations with different researchers in the field, but could you discuss a little bit about your collaborations with the Dutch police and other partners that you've been involved with?
Yeah, that is, to develop such a methodology and to bring it, into the field, such collaborations are essential. So a lot of the research that I do is, it's a little bit of, I call it a little bit of a triangle collaboration. So I need forensic practice because they need to tell me actually how it's done, what are the problems and the challenges. They also can supply me with samples that are from actual casework, right? So not artificially created samples, but actually the stuff that they deal with every day. So that gives me, really valuable samples for me to test and develop the methodology. At the same time, we need companies and technology to allow us to realize the ideas that we have, because if I only if I develop a method in the academic environment, which is the third part of the triangle, right, then we are not product developers. So we are not trained, we are not capable of developing something that is fit for purpose. So I think a lot of innovations fail because of this. That in principle and intrinsically, there's a very powerful method, but the research group involved is just not capable of making the next step into a product that could really make the difference. So then having involved a company that is able to do it, I think these are the three magic ingredients that you need to really be successful. Yeah.
No, definitely, and especially when that company or organization are the people that it's going to be one of the most valuable things is that if you can make a new development, it can. It's another bonus.
Yeah.
So, in practical terms, how easy would you say it is for law enforcement personnel to use the near-infrared-based platform that we spoke about earlier? And I know we've spoken about how the goal is to really make it so that anyone can use the platform, but is there any training that's currently needed to use it?
No, I think a basic instruction would suffice. I think it's that simple. It's basically you have the platform, right? So we use the powder puck, which is like a very small portable benchtop thing. So you put it on the table. Then I would say take a glass vial, put in 0.5 gram to 1 gram of a powder sample, put it on the instrument and press scan, and that's it.
Nice and easy.
Yeah, that doesn't, I wouldn't call that training. It's more like an instruction. It could be in a manual or something. It's that simple, basically.
It's good. It's good then. And bringing it back to your presence here in your presentation at Pittcon, how can this presentation contribute to the broader conversation about technological advancements in forensic science and in the field that you're working in?
Well, I've attended several of the NIJ sessions here. Of course, you hear a lot about forensic science and the advancement in several areas. But clearly, I think there's a lot of interest in portable technology and bringing that analytical technology out of the lab into the field. So I think also when you go out here on the exhibition floor, right, there's an interesting transition, I think, ongoing. So not so much the technology, it is the combination with the computing possibilities that are now there, right? So that allows you to create products that transfer data wirelessly, right? Give results on your mobile phone, connect to a central server where very powerful computers are doing this data science magic, right? Sending back results to the user. And I think that we will see many more of these type of developments, and that opens up a whole range of possibilities. Because in the old days, I think portable Raman has been around for many years already. But you would go into the field with an instrument, and everything would have to happen on that instrument, basically. But now this limitation does not exist anymore, or you can just do the measurement, send the data centrally. You can even have experts looking at the data from a distance and saying, like, yes,
yep,
this meets the quality standards.
Yeah.
Yes, it contains cocaine, and send that result back, and then all in a matter of seconds. So to the user, it's almost like instantaneous, right? But underneath, a lot is happening. So that I think is very interesting development.
Pittcon Perspectives, unforgettable Pittcon moments from the experts.
What are you most looking forward to at Pittcon San Diego this year?
Well, I think the good weather. No, but clearly the presentations and meeting with the scientists is nice, but I think what makes Pittcon very special, that's the exhibition, right? And that is so massive here. There's no equivalent to that in my continent, in Europe or in the Netherlands. And that I find always very inspiring, right? There's all this energy and activity. And especially when it comes to analytical chemistry, it's never only the science, right? There must be the instrumental and technology developments to back it up, to really make a difference. And that is basically what you're seeing happening here on the expo floor. So, yeah.
Definitely. We've had a lot of feedback from individuals like yourselves saying that one of the best things is being able to go out and see the instruments and kind of bring people your problems and figure out how the instruments can help your problems and things like that. I can imagine it's quite exciting. So the final question I have is that as we mark the 75th anniversary of Pittcon this year, could you share your first memory or your first experience of attending this conference and how it's impacted your view of the scientific community, both your own community, but the scientific community as a whole?
This is the third time so it's not like I've been here 75 times.
Still a few times.
I'm getting a bit older, but not that old yet. And the first time, I think I have to remember correctly, 2014, I think, in Chicago, and then in 2017 I also visited Chicago. I remember it was extremely cold, so I'm very happy to be here in San Diego right now. But yeah, it's like, when you go out on the expo floor for the first time, it's just like, it's mind-blowing. I've never seen anything like that before, being an analytical chemist for many, many years. And then you get, like, as you described, you get this feeling of really getting into it, right? Yeah. Talking to people, touching instrumentation, hearing about their great ideas. And also, I think also, it's inspirational if you see other type of applications that can, trigger in your mind. It's like, oh, what would be the forensic angle here, right? Could it be useful? Could I use this to solve a crime? Yes or no? And then you start talking to people and stuff like that. So some of the projects that I'm involved in actually, emerged from these type of discussions.